Alright, let's go to 31 now. Two n-digit integers leading 0 allowed. Oh, that's awesome. Are said to be equivalent if one is a permutation of the other. Fine. Thus, these are equivalent. Mm-hmm. Find the number of 5-digit integers such that no two are equivalent. So if one is a permutation of the other, then fine. Okay. Number of 5-digit integers, fine, such that no two are equivalent. Wait, what does that even mean? Also, like the set containing the. Okay. I think I'm getting it. Okay. Yeah. Okay. Very good. Find number of 5-digit integers such that no two are equivalent. Oh, right. So, you just want to put. So it's like the star bar theorem. I get it. So there are 10 digits, and then you want to. Yeah. So every time a digit appears in our sequence, we'll just put one coin in that I don't know, it's hard to explain, right? In that section, okay, we'll just put a mark for that digit, right? So it's like distributing these marks into these 10 digits, right? Exactly. So then the number of stars are 5, and the bars will be so before every digit is the thing. So yeah, 10 bars, I believe. I guess that should be the thing. Yes, 10 bars. So 10 bars, 5 stars. It's 15 characters, right? 15C5. That's the thing. That's definitely. Wait, no. Okay. The last one you don't even have it. Isn't that right? Oh, right. So it's not 10 bars. It's actually 9 bars. So 5 stars and 9 bars is like 14C5. Got it. So 14C5 ways of doing this. Yeah, that should be the thing. Okay. Number of 5-digit integers that no to have row equivalent. Got it. So these many ways. Which I'll just put it like that. We won't even calculate this thing. Actually, we can. It's not that hard. 14 times 13 times 12 times 11 times 10 upon 5, 4, 3, 2, 1. This cancels. It's just 14 times 13 times 11. So 14 times 13 is like 42 and 14, which is 182, right? So 182 times 11, is that right? It's just 2 0. Okay, just 0 1 carried on, 2 is just 0 1 again. Okay, fine. And 2 0 0 2. That's the thing. Awesome. Yeah, that's how it should be. Okay, next question. I did this correctly, right? I hope so. 182 is. Yeah, it's just 42, 14. It's gotta be 182. Next question. Come on. 32. Alright, use a combinatorial argument to prove that this is equal to 2n-1 factorial upon n-1 factorial squared. So nc1 squared plus 2 times of nc2. Okay. It's a 2 over there and a 3 over there and so on. Interesting. Yeah. And we have to prove this using a combinatorial argument. It's like 2 of these guys and then there's 3 of these guys. Why is that the case? NCN. Where's the N? Okay, it's like 0 NC0, isn't that right? So let's just. I know it should be using a combinatorial argument, but yeah, scrap that. So S is equal to summation of RC0, right? Actually, why even do that? Just write like this thing. So 0 NC0 squared plus 1 NC1 squared, so on till n NCN squared. So then you can write S is equal to, just put this here, so n, but then instead of NCN we'll just write it as NC0 squared, and then like n minus 1 NC1 squared and so on. So n minus 1 becomes 1 and stuff like that, till eventually you get like 0 NCN squared. So then add this, just get S is equal to half of, so n plus 0 is n and everything. So like n upon 2 basically, n upon 2 times this thing, nc0 squared plus nc1 squared, so on till ncn squared. And this thing is actually doable by combinatorial argument. So you can change this. You can write s is equal to n upon 2 times nc0 ncn plus nc1 ncn minus 1 and so on and to ncn nc0, and then this just becomes the number of ways of choosing n people out of out of a group of n boys and n girls, basically, right? But then again, there's like only 2n people. It doesn't matter if they're boy or girl. So 2ncn, that's what it should be. So it's like n upon 2 times 2ncn. Yeah, that's what our sum is. So we want to prove that it's equal to this thing. Easy. It's going to be 2n factorial upon what, n factorial, and that comes of n upon 2. So you can write it like 2n. Oh, okay, so right, 2n times 2n minus 1 factorial. You can write it like that. So this 2 cancels with that, n and n over here, you just get n minus 1 factorial now. Yeah, these cancel with that. So 2n minus 1 factorial, you get n minus 1 factorial squared, because 2 of these guys, and the n's in that will get cancelled from this and that. Easy. So there we go. Next question. It's done. It wasn't exactly completely combinatoric argument, but still some part of it was, so I guess it's good enough. Next question, 33. Tn denotes the number of non-congruent triangles with integer side lengths in perimeter n. Triangles, okay, non-congruent triangles with integer side lengths in perimeter n. Does T1 equal to T2? Okay. Prove that T2006 is less than T2009. Okay, I get it. Integer side lengths perimeter n. Fine. This is gonna be hard, isn't it? So it's like, okay, it's almost like star bar theorem, but not quite. So there's a restriction that x plus y is bigger than z and stuff like that, huh? Yeah, there's that restriction. So then how do we do it? X plus y is bigger than z. We'll just say, okay, the smallest one, we'll just cut that down or something like that. This is still weird. Yeah, very weird. Okay, so go with the thing that there's like 2 largest ones and 3 largest ones. So either you could have all 3 the same side length, right? That's one thing. So n upon 3, isn't that right? Yeah, each with the same side length, n upon 3, n upon 3, n upon 3. And that happens if n is divisible by 3, right? Oh god, this is very weird. So if n is divisible by 3, it should give us that guy. Okay, what do you have to prove? You have to prove that T2006 is less than T2009 and T2005 equal to T2008. So add 3 to the thing and then integer side lengths. This is very weird. 2 which are bigger and come on, think. Isn't there some better way? Algebra representing this thing, probably not going to happen, huh? Yeah, because of that restriction. I mean, the triangle inequality has to be followed, but how do we make sure it's always followed? What kind of structure would allow that? Multiple of 3 or something like that, huh? Come on. Alright, let's just start with 206 and 2009. We'll see what happens. Wait, what's happening? T1, T2, T3, T4 all are 0 while T5 equal to 1. Interesting. Okay, so it's like 2 to 3. I get it. Yeah, well, whatever. Doesn't matter. Okay, so T2006, we want to figure out what is that number going to be and how is that less than T2009. It's like some kind of insertion happening over there, isn't it? Yeah, that's probably not the best way to be doing it. We need actually something to, if you could just calculate what T2006 has to be, that would be awesome, isn't it? Yeah. Like changing the restriction a bit. Oof. This is weird. If you don't do that, we could actually change it like this. Just put those 3 over there and then you start with the same thing once again. Right, you could also have 0 or things like that, huh? And that's still allowed. Oh, this is kind of weird. What if we put all 3 at the same place? So no, a recursion is hard to build in this thing. So then what? How do you even do it? First 3, where do you... Right, you can't build a recursion. You'll actually have to figure out how to do it. Isn't that right? Yeah. So you want to put this into 3 columns such that... this is stupid. It's plus that. Okay. It's bigger than that one. When is that gonna happen? If this plus that, it should be bigger than that. No idea. No idea. Wow. Okay, so it's like this. You got the star bar theorem over there and then, but no, we want the sum to be the thing, right? So this is rather stupid. We want the sum to be the thing, isn't that right? Oh, and some things you just won't allow, right? I don't know how to do this. So for some particular n, how do you do it? Is there some sequence? No, there's probably no sequence at all. We'll just write some stuff down. Hopefully that will give us some insights. This is equal to n, x plus y is bigger than z. Let's assume that z is bigger than x and z is bigger than y, right? So it's the largest one and x plus y is bigger than that. Okay, now how is that gonna happen? You want to split n into 2 sections such that this is still stupid. You don't want it to be like that. You want it to be less than z, huh? No, this is not helping. So x has to be less than z, sure, but y2 has to be less than z. So how are we going to do this? How are we going to do this? Really? I have no idea. So we already assume that z is bigger than x and y. So then, okay, that won't help. That just won't help, huh? Fine. Some other way. Being kind of like a circular way. Yeah, okay, as a circle. So n represents the complete thing, and then what? This and that. Okay. Then again, what's the thing? Z is the bigger. That is the biggest one. Okay, cool. Let's invite smaller ones. No, it's not helping, really. It's not helping. How do we do it? Should I just leave this at this point? I can't think of a recursion. I can't think of anything. Non-congruent triangles with an each side, let's say pyramid n. And how is it that T2005 is equal to T2008? Like for each triangle you can always add 3, sure. And you can also add 2 over there. Okay, yeah, no, this is incorrect. It has to be more, right? It has to be more. Okay, suppose you have a triangle, right? So in the 2005 case, you have a certain triangle. Just add one. Yeah, okay. You add 1 unit to each side, and there you go. You got a 2008 kind of triangle now, right? So all the triangles in 2005, the same are copied to 2008, just with one side length, 1 unit added to each side. But then you can also add like 2 units to some side and then 1 unit to some other, right? What about those cases? Non-congruent triangles, listen. So the factorial stuff should not. Okay. Come on. How do I do this? Assuming the larger side is that. Summed to be bigger than that. This is not making sense. Can't even find a recursion for this. And it just doesn't feel correct. Let's move on. I don't know how to do this. 34 is find number of different ways of painting a cube by using a different color for each face from 6 available colors. Any 2 color schemes are called different if one cannot coincide with the other by rotation of the cube. Painting a cube by using different colors for each face from 6 available colors. Okay, so there's 6 different colors, and yeah, easy, fine. Yeah, again, 2 color schemes are called different if one cannot coincide with the other by rotation of the cube. Fine. So first we'll just call the colors 1, 2, 3, 4 till 6. We'll always take 1 to be the base of the cube, right? And let's think about what's opposite to 1, right? So opposite to 1 there will be 5 choices that you can choose, and then the other 4 those will be on the side walls of our cube. So they're clockwise or anti-clockwise order, right? That's what we are looking for. So let's just think of the anti-clockwise order only. So the anti-clockwise order, yeah, that completely determines the thing. Okay, cool. So then they can be ordered in how many ways? 4 factorial we would think, but that actually upon 4 because it doesn't matter where you start, right? Yeah, because you can always rotate. So just 3 factorial ways to actually arrange them. So those many cubes you will basically get, right? Is the number of ways you can paint the cube. That should be nice. Okay, so 34th is done. 5 times 3 factorial, which is like 5 times 2 is like 6. So 30 ways. Next question, 35. Take a triangle ABC, take n points of subdivision on side AB and join each of them to C. Likewise, triangle ABC, n points of subdivision on AB. Points of subdivision. Okay, so n plus 1 divisions basically. I'm like, okay, n plus 1 parts of our AB side. And you want to join these n points to C. Likewise, take n points of subdivision on side AC. And join each of them to B. Into how many parts is triangle ABC? That's it. That's the whole question. Oh, come on. That's actually pretty easy. So we know that it's not possible that a line connecting this to that is parallel to a line connecting this to that, right? Yeah, that just doesn't feel like it's gonna ever happen. because this will be in this angular range and this will be in this angular range, right? If I just move it, so like this, okay, it's never gonna happen. Sure, you just have to move. Okay, just make a parallel something over here. Oh wait, actually that's not supposed to be. It's more complicated than that. Okay, so this is the range we're talking about. Also, it can actually be possible if this thing is like obtuse. So if it goes like this, then it can in fact be possible. Let me try to draw it. Right, you just have to copy this. Okay, this is still not making sense. It's not possible now. So it's gonna lie outside of it, it seems. That this angle, which is the same thing as this angle, that's actually bigger than this angle. So if it's smaller, then you're basically done. Oh, but that can't be smaller because this plus that is what this thing is. So yeah, it's got to be bigger all the time. Okay, what that means is, yeah, these can never be parallel because these two angular ranges, I'm gonna call them, right? This angular range and where did that one go? This angular range, it's created by this thing. These will be always, you know, non-intersecting, right? There's no way that these two lines can be parallel, right? Yeah, and no three lines. I mean, like there can't be three lines. So all these lines are only intersecting at this point, and all these lines are only intersecting at that point. Can it ever happen that one of these lines will intersect at this point? Well, one point is fixed over there. Other point that lies on this line, okay, if it reaches that point, this can happen, but that never happens really. So yeah, that's not gonna happen that one of these lines will intersect this point or any of these points. So yeah, that means that each of these lines will intersect with each of these lines exactly once for each line, right? And how many lines are there? N. So we'll intersect n times, right? So it will create n plus 1 line segments. Yeah, that's that one and n, right? So n plus 1 line segments, which means it will divide some region into 2, right? And it's like n plus 1 regions into 2, so it adds n plus 1 regions every time. So yeah, each line adds n plus 1 regions, and there are like n such lines, n times of n plus 1. Initially there were how many regions? Just one. Well, no, okay, initially there were how many regions? So n of these guys, right? Yes, there were n plus 1 regions. So to that you add this thing, like n plus 1 squared. That's the thing, which is to be expected. Yeah, that's just how it should be. It's kind of like a warped sheet of paper, something like that. I don't know. Okay, but that's the thing, n plus 1 squared. So what was the question? 35. Yeah, that's our answer, n plus 1 squared. Next, 36. A positive integer n has the decimal representation n is equal to d1 d2 till dm. N is called ascending if 0 is less than d1 is less than d2 is less than, okay, till dm. Okay, so all these have to be bigger than 0. Okay, and it's called strictly ascending if this happens. Fine. Find the roll number of type A and type B numbers which are less than 10 power 9. Less than 10 power 9. Oh, okay, I get it. So you can also have actually zeros. Yeah, okay, I get it. So even though it says that 0 is less than or equal to, right, we'll just think of, okay, so for example, a 5-digit number, you can represent that as a string of 9 characters, right? The first 4 have to be 0. So why not like include 0 in this as well? because then you'll be able to represent 5-digit numbers as well. Yeah, that's just right. This is just to distract you. Really, you can also have equality. Just that number has to be like involving zeros as well and everything. And zero is also a digit. It's in the start. It's kind of weird, but that's how it should be. Okay. For combinatorial purposes, that's how you think of it. Okay, so it's like 9-digit numbers, and when I say that, I'm also including zeros as the starting digits. Okay, so you want ascending numbers first of all, and then you want strictly ascending numbers. So in strictly ascending numbers, you can have a string of zeros at the start, but after that you cannot have equalities. So once it starts, it's like 1 2 3. Yeah, okay, right. So then it's like star bar theorem or something like that. You could think of it like that, sure, but no, this is more than that every time. It's kind of weird. So you have to add something every time, isn't that right? It is almost like star bar theorem. The first one may not even have anything. So yeah, it is a lot like star bar theorem actually. So how many stars do you have? The maximum it can reach is just 9, right? So you 9 stars. And how many bars do you have? So before every number, right? Okay, so we will need 9 bars as well, right? So the thing is like, okay, so for example, if we had 5 stars and 3 bars, right? And yeah, let's say the configuration is like this: 2 bars over here, 1 bar over here, and 1 bar over here. What we would read it as is that before this bar, the number of stars, well, that's 0, so 0. Then after this bar, so before this bar, still 0. Before this bar, there's 1 star. Before this bar, there's 1 2 3 stars. And that's it, that's our number: 0 0 1 3. Oh, these are only, okay, these are like 4 bars. This will be a 4-digit number. When I say digit, I'm including, zeros at the starting point as well. Okay, right? So yeah, this kind of represents our ascending numbers, right? And for them to be strictly ascending, there should not be empty spaces between our bars. You should have stars. You should have at least 1 star between each bar, right? So that's like inserting. Oh, that makes perfect sense. Okay, the first one is very easy. It's just 18C9. Okay, and the next one is a little different. So once again, 9 stars, 9 bars, but now between each bar you must have at least 1 star, right? Oh yeah. Oh, and for the starting bars, you can actually have a star over there, right? Oh, okay, this is kind of different. So you can have empty spaces. It's not like you cannot, but only at the start. Huh, it's weird. So you only have at the start, huh? Fine. So then think of the spaces where you can insert bars. Like, how many ways can you do that? So we can insert in these spaces. Okay. Oh, it's supposed to be 9 stars, right? Yeah. You may not even insert at all, but that's also possible. Okay, let's just go with this example of 5 stars and 4 bars first, and then we'll think of 9 stars and 9 bars. So you can insert in these places. Right, once they're 1, then it has to be 2. And before that, if you insert something, well, before that as well, you can actually insert something, right? Exactly. How many can you actually insert? What's the maximum? Oh, and also, oh god, this is actually not going to be nice. Yeah, it's definitely not nice. this one of choosing places, right? Oh, I see. So what we can do is like, okay, 2 power 9, that actually makes sense, doesn't it? So if we start, right, actually it makes a lot of sense like that. Yeah, it actually does. So just forget about this completely, right? Okay, forget about the bars that you have to put in front, right? Forget about that completely. Just before that, we'll just think of arranging the 9 bars over here, or like in this case 4 bars. So, but it will not be like we have to arrange all 4 bars. It's like we can put bars inside or not. We don't care. So then the number of ways of doing that, what's that going to be? Oh, okay, that's actually still complicated, isn't it? Yeah, it's not exactly like permutation, isn't it? This is weird. This is very weird. Well, then we just go off to casework. So, 1 digit number, 2 digit number, so on, right? So for this case, it will be like first 4 digit numbers. So like you got all 4 bars over there somewhere, right? Then you don't want this. That represents 4 digit numbers. So you have to have 1 at least. You cannot have 0 at the start. Yeah. Wow, this is really bad, isn't it? God. Fine. So then 1, 2, 3, 4, 5. This is just 5C4. Then next you could have 3 digit numbers, right? So just put 3 over there, and it's like 5C3. It's 5C2. It's 5C1. It's 5C0. Something like that, huh? So like put multiple stuff inside. And okay, what happens to the remaining bars? Just put them over here like that, right? So those will be just 0, 0, 0. Yeah, that's the thing. Same stuff goes with 9 stars and 9 bars as well. So we start off at 9 digit numbers, like 9C9. Then we go to 8 digit numbers, 9C8. Then 9C7 and so on, 9C1. And what about 0 digit numbers? We don't think about them, right? Yeah. Is 0 also okay? A positive integer you want, right? Fine. So you cannot have 0 over there. Got it. Hey, in that 18C, oh, okay, so 18C9, well, that also includes a 0, isn't that right? And all the bars on the left, that's gonna represent 0, so this thing -1. The second one, you have this number, which is like 2 power 9 minus 1, and that's our answer, huh? Interesting. I do wonder, why is that the case? 2 power 9 minus 1. I don't know. Why is that the case? Okay, it's like, do you want to shift or not? Something like that. Huh. Interesting. Yeah, I think I'm getting it. I'm getting it a bit. So, at first, there's 0, right? Okay, so let's just think of it like this. You have these 9 places. The starting place, okay, let's just say you have 10 places. The starting place is 0, okay. In the first place, do you want to change? Do you want to increase it, right? So, like, okay, first we have a bar over here that represents this 10th place, so that's 0. Then for the next place, you ask this one, do you want to be included or not, or something like that. I'm thinking of it like that. Okay, so if this guy is I'm not gonna be included, then you put another 0 over there, right? If this guy says I want to include it, then you move it by 1 and then you ask this guy, right? Yeah, I think that's how it should be. Wow, this is getting weird, isn't it? So for every bar you will have to ask, no, this is not making sense. This is not making sense. It's more like asking, do you want to have a bar before you, right? That would make sense, because you cannot have multiple bars before you, right, immediately before you, so you can only either have a bar or not have it. So that's why you are asking, do you want to have a bar before you, and then the maximum number of bars you can get like this is 9. Of course. So yeah, right, think of it. You got these 9 places and then you can start inserting. Maximum number of bars you can have is 9, right? And the remaining bars will just go on the front. Well, that makes sense. Sure it does. And that's why it's 2 power n. Sorry, 2 power 9. Yeah. So it really is like that. You wanna. So in this example, the problem was it was 4 bars, right? So sometimes the configuration will be such that you got 5 bars, which is not making sense. But if this was something else, if this was 5 bars as well, right, then yeah, you could have done that. You could have actually done that. You could also have got 5 bars accepted. Awesome. That makes a lot of. So if the bars are higher, then right, then that makes sense. Makes a lot of sense actually. Sure. So yes, 2 power 9 minus 1. I got it. Understood it in both ways now. 37. Okay. Prove that this summation is equal to n factorial times e minus 1, where this is a step function. You will need the series instead of e. Summation from r equal to 1 to n of npr is equal to n factorial e minus 1. And this floor function of that. Okay, fine. So this is minus 1 integers, you can just take out. So it's like n factorial e, the floor function of that, minus 1. So like 1 plus that. Okay, cool. So yeah, you can actually kind of start from 0. N factorial upon n minus 0 factorial is like n factorial. So that's just 1. So it's like summation from r equal to 0 to n of npr. That's equal to this n factorial e times n factorial. That's what you're saying. Okay. Wow, that's kind of weird. This is the same thing as saying that this summation, well, let's call this s is between n factorial times e, that plus 1, and it's or equal to n factorial times e. Okay. So that's like saying that s upon n factorial, that's less than e plus 1 upon n factorial, and it's bigger than or equal to e, right? Okay, cool. Fine, think about it. So this upon n factorial every single time. NPR, just like n factorial upon, oh, so it's just n factorial upon n minus r factorial, isn't that right? So if I divide by n factorial, just like this thing, so 1 upon n minus r factorial, so on. So r equal to 0 is like 1 upon n factorial, then 1 upon, oh, I get it, till eventually get to r equal to n is like 1 upon 0 factorial, that's just 1 upon 0 factorial, just 1, then you got 1 upon 1 factorial, and so on. So it's still 1 upon n factorial basically, right? That's what this will be, s upon n factorial, and you're saying it's bigger than or equal to e and less than e plus 1. Okay, wait, what? No, this is not making sense. How is this bigger than or equal to e? This is the floor of this guy, isn't that right? Wait, something's not right. Sorry. It's saying S. Okay, okay, this is kind of stupid. So S is yeah, that this is what it should be. S is less than or equal to n factorial e, which is less than or equal to, oh, strictly less than s plus 1. So it's like s upon n factorial, that's less than or equal to e. Yes, it is. And s plus 1 upon n factorial, that's actually bigger than e. Oh, okay. Why is that the case? So, okay, why is that the case? So e would be just 1 upon 0 factorial and stuff. Okay, fine. So 1 upon n factorial. This is weird. This is like saying that 1 upon n factorial, because okay, the rest part is the same, so it's like this is bigger than 1 upon n minus 1 factorial plus 1 upon n minus 2 factorial, so on, right? It's like saying that. Is that correct? I don't know. But okay, the n factorial stuff is there every single time. You cancel some stuff like that. It's not n minus 1, it's n plus 1 factorial. Plus 1 upon n plus 2 factorial, so on. That is somehow less than 1 upon n factorial. That's what you're saying, isn't that right? Okay. How is that possible? Yeah, I don't get it. Let's try to write it, you know. So we'll just write it once again. What we're saying is 1 upon n factorial is bigger than 1 upon, and you know what, actually just remove the n factorial anyway. So just 1 is bigger than 1 upon n plus 1 plus 1 upon n plus 1 times n plus 2, and so on, right? That's what we're saying. Okay. If I can somehow prove this recursively or like inductively, right, then we are done. So let's just say that this is true till 1 upon you start off at n plus 1, you reach till k, right? If this is true, then the next one will also be true or something like that, right? This is weird. 1 will be bigger than that. We can't say that for sure though. How do we know if this is going to work? Come on. And this works for every n you are saying. Okay, let's change this a bit. It's like 1 is bigger than 1 upon n plus 1 upon n times n plus 1 plus 1 upon n times n plus 1 n plus 2. So on, right? Yeah. Come on, think. Why can't I think about it today? These factorials though. Yeah, I don't know. I don't even solve that. It's like, okay, you say like multiply by n and then that minus 1 and n plus 1 over there, okay, and that minus 1 and so on. Actually, let's go on with this. Let's see what that gives us. So multiply by n plus 1 on both sides, right, and then you subtract 1 on both sides, you just get n bigger than 1 upon n plus 2 plus 1 upon n plus 2 times n plus 3 stuff. So then you multiply by n plus 2 and then subtract 1 once again. It's like n times of n plus 2 minus 1, that's bigger than this thing. Yes, that's correct. Then go, yeah, okay, just keep doing it like that, and yeah, this actually will always be bigger than 0, and this is actually approaching 0, right? And this is more importantly some kind of integer, some positive integer, because this only gets bigger, like n times n plus 2, well, that minus 1, it's already large, so then that minus 1, yeah, sure, that's how it should be. But this of course assumes that n is bigger than or equal to 1, otherwise this won't actually happen, right? Yeah. So where's the restriction? Which question is the 37th? Right, so prove that this is happening. And so okay, r starts at 1, so n is assumed to be bigger than 1 already or equal to 1. Cool, then this works perfectly. Yes. So let's just take an example. Let's just say n equal to 1, then it's just np1 basically. Okay, 1p1. Yeah, so 1p1 is just 1, of course, and 1 is equal to the floor of n factorial is just 1, because like e minus 1, which is, yeah, this is correct. Awesome, this makes perfect sense. Sure. So yes, this part is very obvious, and then this part is also true. I didn't think it would be, but it is, in fact. Okay. Next. So go 38. On 38. 38 is, show that the combinatorial number 2ncn is even for all n. So it's 2n factorial upon n factorial. It's like 2n factorial upon n factorial squared, you can think of it like that. And you have to show that this is even for all n. Oh, okay. So it's like 2n times minus 1 all the way till it's like n plus 1. That upon n plus 1, so on till 1, of course. Yeah, it's kind of weird, of course. Okay. We can do it like this. So the number of 2's you will have in the prime vector representation, so prime factorization of 2n factorial, that will be given by this thing, 2n upon 2 the floor of that plus 2n upon 2 square the floor of that plus, yeah, just keep going, right? So let's just call that number as x, and y will be number of 2's in the representation of n squared, so n factorial squared, right? Which is, okay, let's just say y is the number of 2's in the prime factorization of n factorial itself. So that's going to be n upon 2 plus n upon 2 squared and so on. So this number is basically like what? It's just floor of n plus 4 of n upon 2 plus, yes, it's like x is equal to floor of n plus y. So that's just n, of course. So x is equal to n plus y. Isn't that making sense? Yeah. Which means wait, okay, it's supposed to be 2y over there, isn't that right? Wait a second. So n plus y, that's not what we want. Floor of this guy, isn't that right? What we want to prove is like x is bigger than 2y. Okay, let's just think of the number x minus 2y, because 2y is number of 2's in representation of n factorial squared, right? So if x is bigger than 2y, then that basically says that it's going to be even. If it's not, then it's not an integer, which doesn't make sense. And if these are equal, then it's odd, right? So what's x minus 2y going to be? It's this stuff, n plus floor of n upon 2 plus floor, okay, of n upon 2 squared, so on, minus 2 times of y, which is, okay, this times of 2. So 1 y, I mean, just cancels this stuff, and the other y is there, so floor of n upon 2 plus, okay, floor of n upon 2 squared and so on, right? Exactly. So what we want to prove is that this is actually bigger than or equal to 0, right? So it's just n minus, what was the thing once again? N minus floor of n upon 2 plus floor of n upon 2 squared and so on, right? So we want to prove that this is bigger than 0, right? And since this is an integer, it has to be 1 in that case. Yeah, eventually we're gonna get that. So this number, it's strictly less than this number, n upon 2 plus n upon 2 squared plus n upon 2 cubed, so on, because over here, okay, so we already know that this is less than or equal to this guy, this is less than or equal to that guy, this is less than or equal to that guy, but eventually somewhere you will get 0, right? That's the thing. So then 0, that will be less than whatever like small quantity you have, and then as it keeps going on, you just get 0 0 0 0, but over here you keep getting finite quantities, so guess what, this has to be strictly less than that, right? Yeah, after some point it will become like that. This is 0 and this is not 0, essentially it's a positive number, so it's strictly less than that. And what is this number going to be? It's just n times of 1 upon 2 plus 1 upon 2 square and so on, which we know is just 1, so n times of 1, that's this thing. So this means that this number is actually bigger than n minus n, which is 0. So yeah, this number is positive, and because it's an integer, you can see it's an integer. It's like floor functions everywhere, and this is an integer, so that means it's bigger than or equal to 1. So there we go, it's even. Yeah, our x minus 2y is bigger than or equal to 1. So this number, where did that go? At 2n factorial upon n factorial squared guy, where is that? Right, this thing is even, easy as that. Next, 39. Is show that 2 power 3n times 3 power n divides 4n factorial for all n. So yeah, okay, that's the same as saying that the power of 2 in the prime factorization of 4n factorial, that's actually bigger than 3n, right? Well, what is that? Well, you just want to see that, right? That's going to be this thing, 4n factorial, sorry, 4n upon 2, which is 2n, the floor function of that, which is just 2n itself, then plus n, then floor function of n upon 2 plus floor function of n upon 2 power 2 and so on. So this is 3n already, which means, yeah, this thing is actually bigger than 3n. So 2 power 3n is already included. So like 3n is less than the actual power of 2 in this guy's prime factorization, so 2 power 3n divides it. Similarly 3 power n, so just divide by 3, you get like the floor function of 4n upon 3 plus the floor function of 4n upon 9, so on, right? And we just want to show that this is bigger than n. Well, that's pretty easy, because 4n upon 3 is already bigger than the floor of n, right, which is n itself. So yeah, the first term itself is just bigger than n, and then these might also be some stuff. Yeah, next question. Prove that 2 power n divides n plus 1 times n plus 2 till 2n for all n. This looks familiar. So it's like 2n factorial upon n factorial. It's not that hard. So 2n factorial upon n factorial. What's the power of 2 in this guy? It's gonna be just this guy. You know what? It just okay. What's the power of 2 in this complete thing? So for this, first we'll do it. It's just 2n upon 2, the floor of that, plus floor of 2n upon 2 square and so on, and then minus for this guy is going to be floor of n upon 2 plus floor of n upon 2 squared and so on. So guess what? Cancels, 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 and then there's like some infinitesimal stuff going on, but let's forget that. Actually no, because we'll get zeros eventually, right? So actually it does completely cancel. That's awesome, isn't it? That's awesome. So it's just this thing that we get, which is floor of n, which is n itself. So yeah, where is that question once again? 40. So yes, it actually divides it. I mean, and 2 power n plus 1 won't divide this, but 2 power n will. That's the thing. So power. You know what? Just bring some terminology in. It's called the index. The index of 2 in this, that's actually n. Yeah, that's called the index, right? Not something else. Or was it just called power itself? I don't know. I guess it was called the index. Anyway, I'm gonna call it index, even if you don't agree. So the index of 2 in this is n. That's what it is. Next question. Actually, okay, there's only 3 more questions. We'll do it. 41. Prove combinatorically that summation from k equal to 0 to n minus 1 of 2 power k equal to 2 power n minus 1 for n minus 1. Interesting. Oh, so they also gave a hint. Let m be less than equal to n bigger than or equal to 1. How many subsets of 1 to k till n have m as the maximum element? How many subsets of this has m as the maximum? Oh yeah, okay, that actually kind of makes sense. So that would be the total number of subsets itself. Right. Okay. So the total number of subsets is equal to the sum of the number of subsets with m as maximum elements, as the sum runs from m is equal to 1 all the way till n. So yeah, and so a sub m represents the number of subsets with m as the maximum element, subsets of this guy, of course, right? So a sub m is given by 2 power m. Actually, 2 power m minus 1, I should say. Yeah, because last from m is actually going to be there anyway. So 2 power m minus 1, right? And what we are saying is that summation of am from m is equal to 1 all the way till what was I going to say, till n, right? That is equal to the total number of subsets of, so the total number of subsets of this set, right, of the set 1 till n. That's equal to this guy. So that number is, of course, is 2 power n. So 2 power n is equal to this sum, which is like what, summation from 1 to n of 2 power m minus 1, which is the same thing as saying the summation from 0 to n minus 1 of 2 power m, right? Oh, except this is not total number of subsets because it also contains the null set, and over here you're not containing the null set, right? So this is going to be 2 power n minus 1 except a null set, right? Yeah. So there we go. Combinatorically proved that this is correct. Next question. Let n of k be equal to this set. Find the number of functions from n of n. Okay, so right, 1 till n to n of m. So 1 till m. Yeah, number of functions. So each of this has m choices basically. The first one is pretty easy, right? It's just going to be m power n. Second, okay, 1 to 1 functions, right? So these cannot be repeated anymore. So the first guy has like how many choices? He has m choices. The second one will have m minus 1 and so on, right? Yeah. So till m, of course, it's like mpm. That makes sense. Yes. We're gonna permute m into these n boxes or something like that. Yeah, that's how it should be. Okay. Strictly increasing functions from okay, strictly increasing functions. So I think I get it. It's the star bar theorem, isn't it? Yeah, it's the star bar theorem. So 1 till m, which means like m stars, and how many bars? So the first one can be like, you can have 1, and then it can also have 0. This is kind of complicated, isn't it? So it should always have that. Okay. Strictly increasing function, right? And then there's non-decreasing function, right? So they can actually have. So first let's do the non-decreasing function stuff. Okay, cool. So you always start off at 1. You don't have a 0, unfortunately, right? Otherwise you could use this normally. So then you will actually have to do m minus n or something like that. Wait, we don't even know if m is bigger than n. It's kind of complicated, isn't it? Okay, so for each of these we'll just kind of remove it, something like that. I don't know what's happening. They're putting ones over there anyway, but there are m of these guys. It has to be at least one. Oh, then you just have m minus 1 in that case, so there's already 1. So then once you get m minus 1 stars, you add that 1 to it, you get m stars, right? That's how the largest one is going to be. So then it's like m minus 1 stars, right? Because every of these n already have 1 star in them. So then we forget about that completely. Just think about the extra additions, right? So m minus 1 stars. I know it's not making sense to you, but it is making sense to me, and it's personal practice anyway. I'm not explaining anything. Okay, a number of bars that we need. So there are n of these guys. So yeah, n bars. Actually, wait a second. Nah, okay, let's just continue. So what was I doing? Right, n bars, because before each bar the number of stars that you will get, that's going to be the number, an extra number that you'll have, right? Other than the one that you already have. I know, hard to explain, but easy to understand for me. Okay, so then it's just going to be n plus m minus 1 cn. That's that number. So this is actually the fourth one's answer, not the third one's answer. Okay, so for the third one, right, before each bar you are actually going to insert 1 star, because you want an increase of at least 1 anyway. Yeah, exactly. Or you can always insert bars into it, right? So okay, how am I going to do this? Let's think of it like that. You got m stars and n bars. So these are m stars, and you will be inserting it in these places, which are like m places, so that you will have 1 at the start at least, right? And then there's at least 1, there's a difference of at least 1 star every time you go to the next bar, right? There could be a difference of 2 stars as well, so that's also allowed. Yeah, in that way you get all of these, right? So just want to choose places from this. So yeah, strictly increasing functions, well, that requires that m is bigger than n or equal to n, right? Yeah, because otherwise it's not going to work. So the third one is mcn. Nice. So that's 42. Let's go to 43 now. 43 is let 1 be less than or equal to n be less than or equal to r. The Stirling number of the first kind, S of r comma n, is defined as the number of arrangements of r distinct objects around n identical circular tables, so that each table contains at least 1 object. What? Each table contains at least 1 object. Okay, n identical circular tables. Oh god. At least 1. Wait, so you mean like the tables can have... Oh god, this is weird. R distinct object. N identical circular tables. So each table contains at least 1 object. And the objects are distinct as well. Tables are identical though. Okay. This is just weird, isn't it? Yeah. So first we have to show that SR comma 1 is equal to R minus 1 factorial. So that's saying that number of arrangements of R distinct objects around one identical one circular table basically. Right, that's our, okay, we know the first one is true anyway, right? So first one, it's true, we know that. Second one, right, we just do R factorial and divide by R because R rotations. Okay, second is SR R minus 1. So you want around R minus 1 identical tables. This is kind of weird, isn't it? Equal to RC2, then R is bigger than or equal to 2. Fine. Okay, just that extra one guy. So the R minus 1 tables, well, that will be filled. There's that one guy which actually contains two objects, right? That's that one table. So first we have to choose that. So R minus 1 ways to choose that, and then once you have chosen that, right, you'll have to choose two people for that. So RC2, and then you have to put all the R minus 1 people into the other tables. So that's gonna be in R minus 1 factorial ways. Wow, it's weird. And there you go, that's it. Because okay, these are just sitting opposite to each other, so there's no clockwise or anti-clockwise sense. It's still gonna be the same thing exactly. So yeah, that's the number of ways. So yeah, wait, but you are saying it's, oh right, these are just identical tables, which means it doesn't matter which table you choose. So this doesn't matter, you're not arranging anywhere because okay, just selecting R minus 1 people. Isn't that right? Of course. Just yeah, the only thing you have to do is just choose two people, put them on any table, and then fill the rest of the tables with other people, because the tables are all identical. Okay, so that's what they meant when they did it in the last question, right? Okay, so this is RC2. Yeah, so now I understand what's going on. Let's go solve that question. Hopefully we'll get it done this time, or maybe that's gonna be even more complicated now. Now I can't find that question. Okay. I don't see that. Okay, this is still not the same. Okay, that's also doable. It's okay, yeah. Fine, I'll find that and then I'll solve it. So that's it. I'll see you in the next video.